are several statistical models for time series data: Autoregressive AR model, moving average, MA, Autoregressive integrated moving average, ARIMA, also vector autoregression, and hierarchical model. While they all related to linear regression, this model is specific to time series data. You all should be familiar with linear regression and its main assumptions. Linear regression assumes you have independently and identically distributed data. Let's review a couple of assumptions that are important for time series data as well. First assumption, linear. The relation between y and x is linear. You can plot the dependent variable against your independent variable and then visually inspect the scatter plot to check for linearity. Assumption 2, independence. You should have independence of observations. Assumption 3, equal variance. At each value of x, the variance of y is the same. However, in the time series data, points near in time tend to be strongly correlated with one another. So can we use a linear regression to model time series data? In fact, linear regression can be applied to time series data provided you have the following conditions that are met. Assumptions with respect to the behavior of time series. Time series has a linear response to its predictor, and no input variable is constant over time or perfectly correlated with another input variable. Assumption with respect to the error. For each point in time, the expected value of the error, given all explanatory variable for all time periods, is 0. And the error at any given time period is uncorrelated with the inputs at any time period in the past or in the future. So a plot of the autocorrelation function of the errors will not indicate any pattern. And finally, variance of the error should be independent of time. If we have all those conditions met, we can use linear regression to model our time series data. The library forecast and its function TSLM designed for linear regression technique for time series data. In this example, we will use the male monthly death from lung disease in the UK from the library ggplot, mdeath. The TSLM function is designed specifically to fit linear model to time series data. The function calls LM, linear model, to do the estimation, but to display the output to remember the TS time series attributes. It also handles trends and seasons automatically. If you look at the summary output from regression, here do you notice the trend is significant and has a negative coefficient, as well as seasons. We have season 3 is not significant, season 2 is not significant. However, all the seasons from seasons 4 up till season 12 are significant. We can also check for the value of R squared. It's 84%. Now let's decompose time series into seasonal, trend, and irregular component. We'll use function STL and the parameter periodic. We can also look at autoplot of our dataset to see the time series. Now in our STL autoplot, we definitely can observe negative downward direction of our trend. And also we can observe seasonality. So we have data, trend, seasonal, and remainder as the 4 subplots. Remainder of the time series is a residual. If we need to model quarterly data instead of monthly, we will change the sampling frequency of data. Remember downsampling? We do not change the actual rate, but we change the frequency of timestamps. In this case, we use downsampling. We aggregate our monthly data with n frequency equal 4, which means 4 quarters. After applying TSLM with quarterly data, again we're using our model with trend and season, we obtain the summary output that is much more improved. Look at the R squared, 91%. All coefficients are significant and also negative. Let's decompose our aggregated quarterly data to view trend and seasonality. It's on your right. We can still observe our negative trend, and we definitely see a clear picture of strong seasonality effect. Alright, now let's consider a statistical method developed specifically for time series data. For univariate time series data, we can use autoregressive models. If we're dealing with multivariate time series data, we need to think of vector autoregression models or hierarchical models, which will be covered later. Autoregressive AR model relies on our intuition that the past predicts the future, and so we have a time series process in which the value at a point in time t is a function of the series values at the earlier points of time. So we have a constant beta 0 plus constant beta 1 multiplied by the time value t minus 1 and the error term epsilon. The error term is assumed to have a constant variance and a mean of 0. And since we're looking just one time back, lag 1, we use AR1. You notice we have only y t minus 1. AR1 model has an identical form to a simple linear regression model with only one explanatory variable on your right. So if we know the value of beta 0 and beta 1, we should be able to calculate both the expected value of y and its variance, given yt minus 1. There is a more traditional notation actually that we can use to denote the autoregression coefficient. So instead of using beta, we will be using phi to denote autoregression coefficient. To assess the appropriateness of our AR model, we'll begin by plotting the process and its partial autocorrelation function. This function is called PACF, P-A-C-F. So instead of ACF function that find correlation of present with lags, the PACF finds correlation of the residuals. So we should be able to find optimum order of our AR process using the PACF plot, as it removes variation explained by earlier lags, so we get only the relevant features. For our example, we will use demand forecasting data published in the UCI machine learning repository, and link is provided on the right. So what we need to do, we need to identify a cutoff on the order for our AR process. Look at the example plot on your left. Notice there's one value crossing 5% significance threshold at lag 3. We can also use AR function when we need to automatically detect this order without looking at the plot. So when we use AR function for the specific column banking order 2, and when we print coefficient, we notice it stopped at 3. AR chooses automatically the order. So we're going to call function to fit AR3. So if we have AR1, we have only one phi 1 coefficient. With AR2, we have two lags, phi 1 and phi 2, two coefficients. With AR3, we have 3 lags, and so on. Now we can call our ARIMA model, but we will set our order to 3, 0, 0. The order in this function show the components of ARIMA function. The first component is AR component. Since we're not analyzing right now I and MA components, we set them as 0. Now we can check coefficient, and we can also plot ACF, autocorrelation plot. Remember, autocorrelation plot describes how well the present value of the series is related with its past values. None of the values of the ACF cross the significant threshold. Remember, we do not use the first step. We do not see a pattern of self-correlation here among the residuals, the error terms. So this model can be used for forecast and prediction. And forecast and prediction will be covered in the future lectures.